All right, good morning, folks. Welcome to the final day of Build. I hope you all had fun last night at the celebration. And thanks for joining me this morning. I'm really excited to be here. Really excited you're here. So my name is Tiller Beauchamp. I work in the Windows group in security testing. I do security design reviews, security code reviews, penetration testing of new Windows components. And lately I've been focused on building apps, Windows Store apps, and so I'm here to share some of my experiences with you today. We're going to talk about sort of the best practices that you can follow and some tips that you can use throughout the development lifecycle. So this includes everything from design to servicing your application. So first of all, I'm going to explain why you should care, and then talk a little bit more about what trustworthy computing means. So first of all, trust is this thing that you kind of build in the user, right? You provide them with a trustworthy experience when they use your application. And sort of integral to that is also the reputation that the users build in your application, right? So users have come to expect a trustworthy experience. And if you don't provide that, then it can reflect negatively on your reputation. And your reputation is really at their fingertips in the Windows Store, right? They have mechanisms for providing reviews and ratings. And so you don't want to provide a bad experience that causes bad ratings, because that can lead to low app acquisition, which of course you really don't want. So clearly this idea is important, right? We want to deliver a trustworthy experience. Now, what am I talking about when I say trustworthy apps? What does that really mean? Well, it's not something new. I certainly didn't invent it. Actually, Bill Gates talked about trustworthy computing over 11 years ago, and he kind of broke it down into 4 pillars. So pillar 1 was reliability. The app or system should behave in the way that the user expects. The second pillar was security. The app's integrity, confidentiality, and availability should be preserved. The third pillar was business integrity. And this really has to do with being responsive to the community and providing, addressing problems that are reported and just being responsible. And the fourth pillar was privacy. So allowing the user to be in control of their data and being clear about how their data is used. So I'm a security geek, and a lot of the examples that I'll show you kind of focus around the security nature of this problem. But throughout the talk, you'll see these other themes of privacy and business integrity and reliability kind of woven in. For example, when we talk about the telemetry that the Windows Store portal provides you, or being responsive to reports on your application. Okay, so clearly this is an important topic. It's so important to us that we invested heavily in this area, in the platform and in the Windows Store. We provide app isolation, a capability model that communicates to users how an application can access their resources, what resources they can access, and ensuring that the latest security features are built into your application when you compile with Visual Studio. The Windows Store provides an onboarding experience to make sure that applications are hitting a quality bar that users expect. It provides a vehicle for users to provide feedback, to tell you that they love your app, but they wish it could be better in this way. And the Windows Store Development Portal also provides telemetry data on your application, so you can see in the field what users are hitting, which items are most impactful. But finally, you guys, the app developers, are really the third part of delivering confidence to the users. And so you can do that by following best practices and design, implementation, test, and in servicing your applications. So that's what we're going to talk about today. First, I'll go over some of the things in design, both key decisions and also analyzing your design, and then talk about things to do in implementation. I'll cover some code examples, then talk about testing and verification, and finally follow up with servicing and updating your application. So the key takeaway here is really that, trustworthiness is not something that you can achieve with a simple test case or by meeting some requirement. It's something that needs to be built and maintained, just like your app's reputation. So let's look at some of the key decisions. One of the first things you'll consider is which language or which languages to use when implementing your app. And there's a ton of different reasons to choose a particular language. It might be your own expertise. It might be sort of historically what your company has invested in. It might be particular frameworks that you want to use in your application are supported in particular languages. Maybe your experience level. But there's certain classes of security issues that apply to different languages. Now, this slide is a strong generalization here, right? But I wanted to use it to get your attention. For example, in C applications, you have the power to manage memory yourself. And that doesn't come without sort of the responsibility of doing it correctly and the ability to shoot yourself in the foot. And historically, we've seen issues with memory corruption bugs actually being exploitable, things like buffer overflows or format string bugs. So that's something to worry about, right, if you're using C or C++, or it's something to be aware of. And in JavaScript, JavaScript has HTML, it has JavaScript. It's kind of a classic code and data mix problem. Sometimes that data gets interpreted as code, and that can lead to malicious script injection. So if you're using HTML and JavaScript, you have to be aware of that. Now, the good news is that we've accounted for this and built in mitigations that help protect your application against these things. So in Windows Store apps that use JavaScript and HTML, you have automatic script filtering that's applied. In C and C++ apps, when you compile in Visual Studio, you get the latest built-in memory protections. So by no means should you make your choice based on these classes of issues. It's more that you should just be aware of how they apply. Also, in a modern app, you're more likely to choose a combination of these, right? You may implement the core logic in C, but then use interoperability to leverage an existing C or C++ library. And then you have to be aware of the class that applies to that interoperability library. And if you implement the C app, you'll probably use a web view to host some HTML content. So then you have this other JavaScript, malicious JavaScript injection class of problems. So it's really not as simple as the slide shows. Another thing to consider is you're likely to use third-party frameworks when you implement your app. These are things that you'll package along and that will be installed with your application. Keep in mind that some frameworks were built with different security assumptions in mind. So, for example, in the web space, the browser renders HTML and JavaScript. That usually comes over the wire unencrypted. And it's an assumption that if an attacker is sitting in the middle and able to manipulate that data, then they can get script execution running in the app or inside the browser. And that's assumed to be okay because it's the nature of how browsers and the web work. And if you want to protect yourself against that, then you have to use HTTPS. But we'll talk a little bit later about why that's not the same assumption we want to use when developing modern apps. Some good resources for you to check out to see if applications support Windows Store apps are the Microsoft Interoperability blog, the Windows Store app samples online, and also the Visual Studio Gallery has a lot of templates and samples that can show you frameworks and how to integrate them into your app. Another key choice you'll have to make is regarding user authentication. So there's a lot of options out there for you, and there's a lot of kind of policy decisions to be aware of. This is by no means a complete list, but for example, the session timeout is something you'll have to decide. But also keep in mind that the new modern app application lifecycle kind of changes how you need to implement session timeouts. So for example, imagine that you're implementing a bank application and you want your session timeout to be only 1 hour, but you also provide the user the ability to save their password so that they never have to type it each time they log in. Now, in the new application lifecycle model, the user can log in, choose not to save the password, do some work, and then swipe out to another application. Meanwhile, the application may become suspended, and it may be terminated by power management based on resourcing, maybe memory allocation, maybe battery life or power consumption. And so when the user swipes back to the banking application, you want to provide a seamless experience that never feels like they closed the application, even though your app's been terminated. So to do that, remember the user said, don't save my password, but you're implementing a 1-hour session timeout. That means you have to somehow store that session token. And of course, there's a ton of ways to do that. You can just use file APIs, but then you're writing that token into an insecure place on the disk. So I recommend checking out the Windows Security Credentials Password Vault API for this. Traditionally, this is used to store the password when the user selects Save My Password, but you can also use it to store session tokens there. And this provides you a password vault that's specific to your application. It's roamed across the user's trusted devices. And another option you have is OAuth, right? If you can, you want to avoid having to manage the user's password at all. And OAuth provides you a way to do that. It allows a service provider like Facebook or Twitter to provide you access to the user's data in a way that the user understands. They're presented with a dialogue that shows exactly what your application has access to. And at the same time, you never have to manage the user's raw password. So that's really the way to go if you can. Also remember, of course, you never want to transmit user passwords in the clear. Always transmit them over secure channels. So let me talk a little bit about something kind of new, or rather, I want to introduce some new topics on this slide. This concept of exploit value. So an attacker will look at applications and they'll want to pick a juicy target, right? So for example, if your application declares capabilities to access the user's pictures library, their internet capability, their webcam, and their microphone, that's going to be a valuable target for an attacker. Whereas if you simply declare internet access, an attacker that exploits that application and gains control of it won't gain as much. And so this idea of exploit economics comes into play when designing your application. So the lesson there is that you want to use only the capabilities needed when implementing your application. Also related to this is this idea of exposing the WinRT APIs. So the WinRT APIs provide your application with rich capabilities, write files to disk, and access things through the application's capabilities. But this is kind of a complicated, or it's kind of confusing to talk about abstractly, so let's take a look at an example. So in this code snippet, what the application is doing here is a simple XHR to get some content from the web. And then when it fetches that content, it's simply going to call eval on some property that was inside this JSON object. So if you're not familiar, eval here is evaluate, and it just takes this string value and executes it as if it was code. So what this does is it's taking content that came across the wire unencrypted and then evaluating it. Now, if an attacker is able to manipulate the response from this request, he can control what code is executed here. And the code here has access to WinRT APIs, access to your application's resources and capabilities that the app declares. So clearly that's bad. We don't want that sort of thing. Let's take a look at an example that's a little bit less clear. Here we have a similar thing. An application is fetching data from the web, but instead of just simply evaling it, it's doing a switch statement on some API number. Right? And based on that API number, it's calling some WinRT function. In this case, create file async. Now you can imagine that case 1 here might be read file, and case 2 might be delete file. So in a sense, we're still exposing WinRT APIs to the web in a controllable way. Now, if you're paying attention, you might be thinking, well, that kind of becomes blurry at some point, right? I mean, at some point, these apps are data-driven by nature, and so data inherently is going to influence the code paths that you run. So where do you draw the line? And there's not really a clear answer to that. You have to think about how it can be abused. What could a hacker gain from abusing that functionality? So here we get into kind of analyzing the design. We've finished our initial design. Maybe we've prototyped some stuff, but we want to evaluate it and make sure that the design is trustworthy. Now, it turns out that sort of when you have to answer this question about, can the app be abused, it's very helpful to understand what the attack surface of your application is. Now, the attack surface is simply the portions of your app that are exposed to abuse. And you can think of this in terms of the inputs to your application and the outputs. And we kind of have this bonus with modern apps in that their attack surface is indicated to us by the extensions, the app contracts they declare, and their capability usage. So it turns out that most of the problems we see in apps fall into sort of these 3 buckets here. Assuming that data is trusted when really it isn't, failing to protect data in flight or in storage, or turning off built-in protections. Now, you can easily avoid these problems by simply understanding your attack surface, thinking about those threats, and then addressing them. So let's take a look at a simple example here. This application is a game app. It simply allows the user to save their game and then restore their game later. It reads and writes data to the app data directory. So the app data there is a data store, and the dashed circle is your app process. So this simple example really has no attack surface. There's no way that the app data is going to attack our application. Now let's take a look at a little more complex example. In this case, we have a note-taking app. It allows the user to write notes that get synced up to the cloud. It authenticates the user. It syncs changes down from the cloud. It reads cache files to disk. And also it implements the share target, or a share target. So it takes data from a share source in the form of images, HTML, text, and allows the user to save that as a note. So for example, they may be browsing with IE and then click the share charm and then select the note-taking app, and that data is then sent to the note-taking app. So here we have much more interaction with our application. And we have to worry about, is this data trusted? Is this transmitted securely? Can this data be manipulated in flight? So what we're doing here is really called threat modeling. It's the idea that we're going to look at our attack surface. We're going to enumerate threats, like what could go wrong on each of the data flows. Then we'll identify existing threats that protect against or existing mitigations that protect against those threats. And in cases where there's not an existing mitigation, we'll need to design our own and build that into the app. Finally, during testing, you'll want to validate that the mitigation works. So when you're performing this sort of threat enumeration, there's taxonomies out there like Stride to help you categorize threats and to brainstorm threats. And so here Stride stands for spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. So you can read more about threat modeling in Stride online. Just go Bing it. So I mentioned this before, but the attack surface of applications is really, of modern apps, is more well-formed than classic applications. They run inside of a container, they're isolated, they have app contracts. And so we can pretty easily understand what the attack surface is by sort of these main categories. Opening files, any file parsing is an attack surface. Consuming data from the web is an attack surface. Any contracts you implement, share, actions, search, and then extensions, protocol activation, if your app implements a custom URI scheme. Untrusted data can be passed in there. File activation, similar to opening files, you can associate your app with a file type, like myapp, like .myapp or .jpeg. And that becomes another vector for untrusted data into your application. So let's take a look at what this looks like visually. Now this is kind of a complex diagram. There's a lot going on here, so feel free to take a minute, sip of coffee. So I'll start by explaining what's going on in the beginning here, or in the middle here. This app local context and process, that's your application. That's all the code that was packaged in your AppX, went through onboarding, and later was installed by the user onto the system. Here you have the app data state store that I talked about earlier, and then data flows to read and write that. Now notice these red dashes are new, and they're not between the app state and local context. That's because these guys trust each other. Once you have a data flow that crosses between an untrusted entity and your application, then you have this red dash line to indicate that there's a trust boundary. So that means there's a difference between the privilege level of this guy and the privilege level of your application. So let me talk about kind of the next most familiar thing here, which would be communicating to the web. Here we have an external interactor that's a web service, web portal, maybe a web API, and your application gets and receives data from that. Now, you'll notice the trust boundary there. The reason we put this here is because, you know, this external entity could be someone else. It could be content from the web. It could be manipulated on an untrusted network on the way to your application. So we have to worry about those things. Now, up in the upper left here, we have brokers. And so these are platform components that are trusted, but transparently pass data from other sources to your app. So examples of that are the share contract, search contract, protocol activation, file association. The file picker is a broker that passes, files into your app under the direction of the user. And then new in Windows 8.1 is action targets. There's been some sessions on actions, which are the people and calendar events. It's kind of a task-oriented way to implement things that might have previously been implemented using protocol activation. So again, we have this trust boundary here because although we trust brokers in general, right, they're part of the system, they're passing data to us transparently. We have to make sure that we handle that appropriately. Down at the bottom, we have the documents library. This might be music, pictures, downloads, or any file that the user opens through the file picker. On the right side is web context. So this is content that's loaded in a web view or an iframe inside of your application, but it actually comes from a remote source. So you can have content that's loaded in your app that comes from the installation directory that was installed with your app. It gets loaded in local context. But things loaded from the web are automatically loaded in web context. And we put a trust boundary here to indicate that we don't trust this stuff. And so I want to talk a little bit more about this nuance here. there are some key differences between what we call local context and what we call web context. Local context turns out to be much more powerful. And so this simple chart highlights some of the differences related to the security aspects of these two contexts, but not all of the differences. First of all, the local context has access to all the WinRT APIs and all of the capabilities that your application declares, such as internet client, such as certificates, pictures library. Web context does not have access to those APIs or those resources. The local context can issue HTTP or XML HTTP requests to any domain, right? So the web context can't do that. It's restricted by the same origin policy. Local context is not. The local context can only load scripts from your application and the scripts that were installed with your app. It cannot load scripts that are referenced externally. So if you do a source script tag with source equal to, it cannot be a remote source in local context. Finally, because of sort of the enhanced capabilities that local context has, this mitigation of preventing script injection with automatic script filtering is applied in local context, but it's not applied in web context. So keep these things in mind. The takeaway there is really that local context has a lot more permission and a lot more capability than web context, and you should protect it as such. So let's take a look at an example of this threat modeling concept. Let's imagine that we designed our app, we looked at the attack surface and saw that we're implementing protocol activation. We have a custom URI scheme, Contoso app, :whack whack, save content, URI equal to foo. So let's imagine that our application will, fetch whatever content is at this URI and then save it locally. So in brainstorming threats, we may think, well, what if a malicious web page invokes our URI scheme with untrusted content in this URI? Then that content is then saved to the application. This may lead to spoofing threats or phishing the user or something else malicious. So the mitigation that we want to implement here is to validate this URI when it's passed into our application and make sure that the domain of that URI is something we trust. It's contoso.com, our website, or it's prosware.com, some partner that we trust. So really, this threat modeling exercise is a brainstorming exercise, and you should use it for the value that you get out of it. If you find yourself making up things that don't make sense, you've probably gone too far. So keep it relevant, keep it simple. Your goal really is to understand what could possibly go wrong, how your application might be abused, and then build your application to be resilient against that abuse. Okay, so let's talk about implementation. Sorry, skip the section slide there. So what do we do when we're implementing an application? Well, I would encourage you to follow some kind of design pattern that you like, something that forces you into building testable code. Now, why is that important? What is testable code? Well, if you think about it, testable code has well-defined inputs. It's easy to set up the state. It has outputs or state that's easy to measure that will tell you if functionality was correct or incorrect. So imagine a function that has input parameters, that has output parameters, and you can determine the correctness of the function based on the input and the output. A real simple way to understand this is by looking at what test-driven development does. In test-driven development, you build your test cases first. You build unit test cases first. And then, initially, all your test cases are failing, right? Because you haven't implemented your code. And then you go fill in the functionality of the application, and gradually your test cases begin to succeed as you implement them. And if you follow that pattern, what you end up with is code that's very easily tested. And this is important because it can be easier to debug, easier to implement fuzz tests, which I'll talk about later. And there's also some good patterns out there like MVVM, which separates the functionality of your application from the presentation. And this is important in applications that we have today that have this seamless user-driven experience where they're clicking on maybe the share charm. So these scenarios that they act out are very UI-driven. And MVVM allows us to kind of separate the functionality that's behind that from how it's triggered in the application. In fact, you might have seen this magazine floating around the hallways in stacks. And the second article here talks about MVVM and specifically how you can implement unit tests to validate things like the share charm. So there's a lot of paradigms out there. I think you should follow something that you like, something that helps you build elegant code. It will make it easier to test and easier to debug later. Also, there's built-in mitigations in the platform. You should use them. When you compile with Visual Studio, you get things like stack guard, like safe exception handling, address space layout randomization, all of these memory protections built in. And when you're building a Windows Store app that uses HTML and JavaScript, you get automatic script filtering applied so you don't accidentally inject malicious script into your application. The good news is that it's really easy to use these things because they're on by default. So just don't turn them off. So we've talked a lot about sort of untrusted entities or handling data from sources that might be untrusted. A good rule of thumb to use is that data that's not packaged with your application should be considered untrusted. Data that comes from a remote source should be considered untrusted. Keeping in mind that files saved locally could have come from a remote source. Files in the documents library could have been saved by the user from a remote source, or the downloads folder obviously can contain remote data. Keep in mind that data transferred over the wire could have crossed untrusted networks and been tampered with. It's important that our application is resilient against manipulated data. Otherwise, we might run into problems with script injection or classic memory corruption flaws. So again, the sources for untrusted data can come from files, from protocol activation, from sharing sources, from action sources, any web content, or messages from iframes or web views. So how do you handle untrusted data? Obviously, you're going to have to deal with it, right? By and large, you should leverage platform APIs that are available to you. These are APIs that are hardened against unexpected data. So, things like JSON.parse for handling JSON data, or the built-in XML parsers. When applicable, you can validate the source of the data, for instance, when handling messages from frames. You can also sanitize or verify the format of untrusted data to make sure it hasn't been tampered or doesn't have an unexpected format. Another tip you can try is, when you're coding your application, indicate that some variable is untrusted, that it contains untrusted data. You might do that with just a simple source code comment, or you might do that with some variable naming convention. So let's take a look at an example here. Here we have some code that's setting up an event listener. It's going to handle messages that come from an iframe. And the way the application's built, it may assume that the intention may be that only my content from my application, from my web server, is loaded in that iframe. But in reality, that iframe can go navigate anywhere. So when it does that, some other website may be sending me messages. So it's important that my message handler, validates the origin. And it's actually really easy to do. E here is the event that you're getting. Origin is a property. You can just check the domain, make sure it's equal to what you expect. Also notice that here we're transferring this over HTTP, so this is unencrypted. It could have been tampered with, so we go ahead and we sanitize that this toStatic HTML function will strip out any content in e.data that could be dynamic, such as a script tag or an on-click or on-error property of a tag. So here's another example of sanitizing data. This is implementing the share source. So here we're taking in HTML content from the share broker. And then see here I've marked my variable with untrusted to indicate that it's from some untrusted source. But then I call get static fragment on it, which will do a similar thing to toStatic HTML. It'll strip out any dynamic content. And I end up with S or safe underscore HTML fragment. So then I can go ahead and insert this into some elements in my document without worrying about dynamic script injection. Or rather, right there. So here's something that's new in Windows 8.1. The web view allows you to navigate to local content stored in your app data directory. Now previously, you'd have to do something where you fetch content, you saved it using file APIs, you read it back maybe into a blob or into some sort of stream, and then injected it into the DOM of an iframe. In Windows 8.1, you can use the MS Apex data URI to navigate straight to that locally stored data. Now, one thing to be aware of is that when you're saving this content from a remote domain to your local directory, the origin of that domain becomes the directory that you saved it to. So that means it's really important to save data from different domains to different directories. That way we can preserve the same origin policy. So to explain that in code, here's what could go wrong. This is pseudocode here in order to fit on the slide, but the basic idea is that page 1 is some content from contoso.com, page 2 is some advertising content. And in this example, a folder is created called My Saved, and let's assume that both these pages are then saved into that directory. Now this web view is navigated to this add content. The add content has the same origin as the page 1 that we wrote to the same directory. Now that's bad because the script in page 2 is now able to access resources from page 1. Now imagine if page 1 was your HTML or rather was webmail or was some bank data. Obviously this would be bad. So switching gears here, another kind of tip you can use in your application is self-signed certificates. So if you've ever kind of set up your own web server, generated your own CA and your own private key and certificate, you'll be familiar with this concept. So what this allows you to do is use your own certificate without having to rely on an established chain of trust, some other centralized certificate authority. So the idea is that you create your self-signed cert, you install the key, the private key and the cert on the server, and then you package the cert with your application, and there's some things in Visual Studio you do, and I'll show you that in a second. And then that certificate, when your application is installed into a private store for your app, so that when your app is communicating to servers that use that cert, you won't get an untrusted cert warning. But it's also not installed for the rest of the system or the rest of the apps or for the browsers. So really easy to do in Visual Studio. You just go into your declarations when you open up your Apex manifest file. And here you can see supported declarations as certificates. And then you have a few flags there, exclusive trust, auto select. Here's what it actually looks like in the raw Apex XML file. So again, what that allows you to do is not have to rely on an established CA. But if you're just kind of doing the default thing and all you really want is encryption, then the easiest thing to do is go with the standard a standard trusted CA and purchase a certificate. So some other tips to talk about here. There's resources on MSDN. There's a WinRT API for helping you easily encrypt data and store it. There's another form of HTML or HTTP XML request, sorry, XML HTTP request that allows you to access or to send requests to other domains without passing along the cookies. So remember, the local context in your application doesn't have same origin applied to it. So you can send requests to any domain. And when you do that, you don't always need to pass along the user's cookies. So XDomain request gives you a way to do that. Also, just check out MSDN. There's a lot of other tips on building secure apps there. Now, cool, let's talk about testing and verification. So briefly, some principles. Obviously, your test should be thorough. Complete coverage is really important. Your tests should be repeatable so that you can run them cheaply, easily. If you make changes to your application, you want to make sure that you didn't cause any regressions. Finally, you should have your tests written in a way that's easy to extend them. They should be easily organized so you know where to put new tests as you extend and update your application. Now remember, in our design analysis section, we were talking about identifying mitigations that may need to be implemented. When testing, it's really important that you verify that those mitigations actually work, and also that they cannot easily be bypassed. So remember our example about our custom protocol activation scheme that we're implementing, Contoso app, save content. Here's some test cases we might try and use to validate the implementation of this. Imagine that our validation of the domain was just looking for a substring contoso.com. That'd be really bad, right? But here's an example where you might test for that, where you have a URI that points at evil.com, but then contains Contoso. And then here's another variation, right? You can imagine the case that it's looking for the existence of http://contoso.com. So you might try some trickery with putting that string in the query string of some other URI. And finally, you might leave off this whack internally to try and fool the validation. Now, during verification, you should also validate that the attack surface of the application hasn't changed. A lot of times you'll see apps designed one way, and then through implementation, the design kind of morphs or is extended. And by adding in new attack surface, you can expose the application to new threats, and they may need new mitigations applied to them. So again, you can look at the AppX manifest file, the capabilities, the contracts that are declared, the extensions that are declared, and quickly understand what the attack surface of the application is. Have some fun with this. Try hacking your app. Kind of forget about the design of the application and take a black box approach. Pretend to be the attacker and pretend that you're trying to exploit the user. So some things you can try here are pick your favorite web proxy, record the traffic that goes between your application and between the internet. Look for data that's maybe sensitive to the user that's being transferred unencrypted. You can also do things like some web proxies will allow you to set up automatic manipulations of incoming traffic. So you might pick a keyword that occurs a lot in your application and substitute that with HTML markup or unexpected characters, and then see how does your app handle that. Is it resilient to the unexpected input? Does it crash? Does it manipulate the markup on the display? Those could all be indications of problems. You can also take a look at the settings that your application exposes in the settings charm and ask yourself, could a user configure my application in a way that it becomes insecure for their experience? And is that really something that I want to support? Another important approach is performing code reviews. So you can look for dangerous coding patterns like use of eval or instances of turning off mitigations like execute unsafe local function that will turn off automatic script filtering in local context. So review those and make sure that these aren't operating on untrusted data, or if they are, that the data is being properly sanitized. You should review things like script notify or post message to make sure that origins are properly validated and that and that data is properly sanitized. And in native applications, there's a whole list of APIs like string copy, mem copy, sprnf that can be dangerous if not used correctly. And so you can look for instances of those in your application as well. Also, you can look for kind of security positive functions like toStatic HTML. And you'll want to make sure that there's not some corner case or error path that allows this sanitization to be avoided. Also, fuzz testing is something that you should do during verification. If you're running native code that implements media file parsing or maybe protocol parsing, these things are kind of inherently dangerous when implemented in native code. So fuzz testing is a topic all on its own. So I'm not going to go into a lot of detail here, but to give you a basic example of implementing a file parser, you would take a known good file and then manipulate it, maybe through just byte manipulation. So imagine writing something that picks a random byte in the file and changes it. Or maybe it picks random bytes in several spots in the file and changes it, and then feeds it to the application. And then you want to make sure the application handles that in a resilient way. It doesn't crash. We talked about building testable code earlier, and this is where that can really pay off, because handling file I/O or network I/O can be slow, but if you're able to implement API testing, API fuzzing instead, you can get much better performance, many more iterations, much better coverage of your functionality. Finally, document your results. If you ever come across a case where you missed something, you want to know how you missed that so that you can fill that gap. And it's hard to do that unless you documented what you did in the past. So here's a short checklist. These are just some things I came up with based on my experience. It's by no means a complete checklist. There was another session given by Gus on onboarding in the fast lane to onboarding. So if you're curious about a more complete list, you should check that out. Obviously, running the Windows App Cert Kit is something that will give you a better onboarding experience. A lot of times we see folks add private networking capability to their applications in order to support testing in kind of their enterprise. Make sure to remove that if you don't need it before you onboard. Also, strip out metadata from your images. Like, if you took the image yourself, it may contain GPS data. So probably a good idea not to distribute that broadly. Of course, remove debuggable code and avoid publishing minified scripts or obfuscated code in your app. This will usually trigger warnings during onboarding. And the minified scripts, they don't provide you the same benefit that they did in classic web service base. They're not saving you bandwidth because they're installed locally. They also kind of make your telemetry and debugging in the store more difficult. So let's talk about servicing. You're going to have a lot of reasons to update your application. There may be new features you want to add to stay competitive. Maybe you want to address user feedback or improve the reliability or security of your application. The Windows Store Developer Portal gives you a really nice representation of issues that are being hit in your application. So it surfaces common crashes, common JavaScript exceptions, and common app hangs. So this gives you a really actionable way to improve the reliability of your application. Keep in mind that some of these issues could be security issues. So if you implement native components, pay attention to any crashes you see that indicate read AVs or read access violations or write access violations. These are sort of exception classes that you can see in the crash dumps when you open them up in a debugger. In a JavaScript app, pay attention to any exceptions that indicate dynamic content injection. That can be an exploitable issue. Keep in mind that only your top occurring issues are surfaced in the portal. So by drilling those down, you can get to sort of the longer tail, which may include security issues. If you're implementing or if you're packaging third-party frameworks with your application, make sure to follow their announcement lists. This may be something as simple as subscribing to their Twitter feed or a mail list, because they may also publish updates that include reliability, privacy, or security fixes that you want to take advantage of in your application. Now, here's where we talk a little bit about sort of that business integrity, right? It may be the case that folks come to you and say, hey, well, I found this security issue in your app. Here's how it works. Be respectful and professional with those folks. They're the good guys. The bad guys are the ones that don't come and tell you about the issues in your app. So, respond in a timely manner and mostly plan resources to triage and fix issues. It may be the case that a third-party researcher comes to us or that we become aware somehow of issues in your application, so we can help coordinate communication about issues like that with you. If you find someone coming to you that's reporting an issue and you find that it affects other Microsoft products or maybe the platform, please let us know. You can email us at secure@microsoft.com. So in conclusion, we talked about kind of key design choices, some analysis you can do with attack surface threats and mitigations. We talked about the importance of building testable code, using built-in mitigations, and tips for handling untrusted data. And in verifying, we talked about how to test the mitigations you implement, just hacking your app, things to do in code review and fuzz test, and finally servicing. Leverage the rich telemetry that's in the Windows Store Developer Portal. Plan for security response, plan to update frameworks that you package. So I have a number of resources in the slide deck here with links, so when you see the deck online, you can easily get to these or kind of just search around for trustworthy apps in security and apps. Here's a second. All right, folks. Thank you very much. If you have any questions, we have microphones in the aisle. Thank you. Yeah.
Yeah, hi, Justin Angel. A question about not shipping obfuscated or minified code.
Mm-hmm.
What was my question?
Yeah, well, so you got to remember that the bad guys are going to ship obfuscated code.
Mm-hmm.
So I'm not saying that I absolutely shouldn't do it, but I'm just saying that during onboarding that may be something that's noticed. So if you're a good guy, well, you may not have to worry about it. But also keep in mind that if you minify JavaScript, what are you really trying to achieve with that? If you're trying to achieve something besides performance, well, there's plenty of pretty printers and really good reverse engineers out there that can handle that kind of stuff. So you're not buying security by doing that.
Yeah, maybe a slightly more general question around that is, it seems like this talk hasn't addressed any of the security concerns around the code being non-secure. Like I can change XAML on the disk or XBF in the latest versions, and I can inject JavaScript into Windows 8 apps. What's the security mitigations for those?
Well, so the question is really about, a user can manipulate. Let me try and rephrase this and make sure I'm understanding you correctly. The user is able to manipulate applications that are installed, or maybe a classic applications and able to inject JavaScript into a modern application, right? So that's true. The security model is it's not a castle, it's a jail, right? It keeps these applications isolated from each other. But if you're a classic application, you're running as the user. You're running as medium integrity level. And so you already have way more permission to manipulate the system. So that includes the ability to manipulate applications.
But isn't it true that some applications have data they don't want to expose to everyone? Like if I'm a game and I'm selling my levels for $5, I'd like to make sure that it's gated by the $5 payment?
Yeah. So that, I think there are some other folks that would be better at answering your question there. Anything else? All right, folks, thanks a lot for coming this morning. Hope you enjoy the rest of the day.